Compressors are used in industrial facilities to increase the pressure of air or other gases. The basic types of compressors are positive displacement compressors, centrifugal compressors, and axial compressors. When centrifugal compressors and axial compressors increase the pressure of a gas, they first increase its velocity. The gas is then slowed down and its velocity is converted into pressure. Centrifugal compressors and axial compressors have a number of industrial uses. Typically, they can deliver gases at higher flow rates than positive displacement compressors. Centrifugal compressors operate under the principles of centrifugal force. This force, which is created when an object spins, pushes outward from the center of the spinning object. We can use a simplified illustration of a centrifugal compressor to see how it works. The compressor's main internal components are an impeller and a volute. The volute is a continually widening chamber that is connected to a gas discharge line. The impeller rotates during operation. Gas that enters the compressor at the center of the impeller is swept up by vanes on the impeller and moved outward by centrifugal force. This action increases the velocity of the gas. When the gas leaves the impeller, it enters the volute. In the volute, the gas expands and gradually slows down as the chamber widens. As the gas slows down, its velocity, or kinetic energy, is converted into pressure. The gas reaches its maximum pressure as it is discharged from the compressor through the gas discharge line. In contrast to the operation of a centrifugal compressor, gas flow in an axial compressor travels along a rotating shaft. As shown in this simplified illustration, the main internal components of an axial compressor are rotating blades, which are attached to a shaft, and stationary blades, which are mounted around the shaft. During operation, the rotating blades spin like the blades of a fan. They draw gas in and accelerate it to increase its velocity. The rotating blades then push the gas towards the stationary blades. When the gas contacts the stationary blades, they cause the gas to change direction as it flows toward the compressor's discharge. This causes the gas to slow down. As the gas slows down, its pressure increases. Two kinds of centrifugal compressors are single-stage compressors and multi-stage compressors. Let's look at single-stage compressors first. This simplified illustration is a side view of a single-stage centrifugal compressor. The compressor's main components include a shaft, which is connected to a motor, seals, a shaft bearing, an impeller, the compressor casing, which contains a volute, a suction line, and a discharge line. The shaft is used to rotate the impeller. This one is powered by an electric motor. The seals prevent gas from leaking out of the compressor and lubricant from leaking out of the bearing along the shaft. The shaft bearing supports the shaft and allows the shaft to rotate. Now let's look at a single-stage centrifugal compressor from the suction line side to see how it works. In this illustration, we can see the impeller, the suction eye, which is the area in the center of the impeller, the volute, the suction line, and the discharge line. The impeller consists of a series of vanes. The tips of the vanes that are closest to the shaft are called suction vane tips. The tips of the vanes that are farthest from the shaft are called discharge vane tips. As the impeller rotates, gas is drawn in through the suction line to the suction eye. The movement of the gas through the impeller creates a relatively low pressure in the suction eye. This low pressure, in turn, draws more gas into the suction eye. At the discharge vane tips, the gas is traveling at its maximum velocity. From the discharge vane tips, the gas moves into the volute, where it expands and slows down. As the gas slows down, its pressure increases. By the time it reaches the discharge line, it's at its maximum pressure. Now, in a compressor with a volute like this one, the gas in the volute creates a force called radial thrust, which tends to push against the impeller. Radial thrust is created by the difference in pressure that the volute creates from one side of the impeller to the other. Some centrifugal compressors are designed to minimize radial thrust by using a series of plates or vanes called diffuser vanes. In this type of compressor, the impeller is surrounded by the diffuser vanes, which are stationary. The distance between the outer tips of the vanes is greater than the distance between the inner tip. The vanes create a series of small volutes all around the impeller. So as the gas leaves the impeller and flows between the diffuser vanes, the gas slows down and its velocity is converted into pressure. The series of small volutes helps minimize radial thrust by equalizing the pressure around the impeller. The pressurized gas is then directed into the discharge line. In general, single-stage centrifugal compressors produce fairly high gas flow rates, but their discharge pressures are relatively low. In systems that require higher discharge pressures, multi-stage centrifugal compressors are typically used. This simplified illustration is a top view of a multi-stage centrifugal compressor. The compressor has 3 impellers, 2 intercoolers, a suction line, and a discharge line. There is a volute associated with each impeller. During operation, gas enters through the suction line into the first impeller. The gas passes through this impeller and the associated volute where its pressure is increased. The gas is then directed through an intercooler. The intercooler is a heat exchanger. The intercooler removes heat from the compressed gas. The gas is then directed into the second impeller and second volute where its pressure is increased even more. The gas is cooled by a second intercooler and then directed into the third impeller and third volute where its pressure is increased again. When the gas finally leaves through the discharge line, it's at a much higher pressure than it would have been with only a single stage. In a multi-stage centrifugal compressor, the number of stages indicates the number of times that gas is compressed. It also indicates the number of impellers and volutes that the compressor contains. For example, the multi-stage compressor we looked at had 3 impellers and 3 volutes. That makes it a 3-stage compressor. An axial compressor gets its name from the fact that gas flows through it axially, that is, along its shaft. As shown in this simplified illustration, an axial compressor's main parts typically include a shaft, bearings, seals, rotating blades, stationary blades, a suction line, and a discharge line. Each set of rotating blades, followed by a set of stationary blades, is called a stage. This compressor has 3 sets of rotating and stationary blades, so this compressor can be called a 3-stage compressor. In this compressor, there is also a set of blades near the suction line that pivot. These blades are referred to as the inlet guide vanes. The inlet guide vanes control the flow of gas into the compressor. Closing the inlet guide vanes decreases the flow of gas into the compressor. Opening the inlet guide vanes increases the flow of gas. During compressor operation, gas enters the suction line and passes by the inlet guide vanes. The gas then contacts the first set of rotating blades. The rotating blades accelerate the gas and push it toward the next set of stationary blades. As the gas is pushed through, a low pressure is created in the suction line. This low pressure draws more gas into the compressor. In some cases, these stationary blades can also be opened and closed to help control gas flow. As the gas passes by the stationary blades, it slows down, which increases its pressure. After the gas passes by the stationary blades, it contacts the second set of rotating blades, where its velocity is increased again. From these rotating blades, the gas moves by another set of stationary blades. Again, the gas is slowed down, which increases its pressure even more. The gas is then directed toward the next set of rotating blades. This process continues as the gas moves through the compressor and then out through the discharge line. In this topic, we looked at the basic operation and components of centrifugal compressors and axial compressors. Among the important systems and components that compressors need in order to operate are a lubrication system, seals, and bearings. A lubrication system reduces friction between a compressor's moving parts. Without some type of lubrication system, some of the compressor's parts could be destroyed. Compressors generally use oil as a lubricating fluid. The function of a compressor lubrication system is to provide the compressor with a continuous supply of clean oil at the proper temperature. This is a simplified illustration of a compressor lubrication system. The system includes an oil reservoir, an oil pump, an oil filter, an oil cooler, and oil lines. Oil for the lubrication system is stored in the reservoir. During operation, the pump draws oil out of the reservoir and moves it through the rest of the system. A screen on the pump traps large solid particles and debris. From the pump, the oil goes through the oil filter, where dirt and other smaller particles that were able to pass through the screen are removed. If these materials are not removed, they can get into the compressor's moving parts and cause damage. From the filter, the clean oil flows to the oil cooler, which is a small heat exchanger. If the oil is allowed to overheat, it breaks down and loses its ability to lubricate. Cooling the oil prevents this from happening. The oil then flows to the compressor, where it lubricates bearings or other moving parts. The oil then flows back to the reservoir. The next components we'll look at are seals. Several types of seals can be used to prevent leakage inside a compressor and out of a compressor. A mechanical seal consists of a rotating element and a stationary element that can be used to form a seal between a rotating shaft and a stationary housing. A labyrinth seal consists of a series of ridges that create an intricate path that makes it difficult for leakage to get through the seal. This is a cutaway of part of a labyrinth seal. Both mechanical seals and labyrinth seals may be used with a seal oil system. Some compressors rely on a seal oil system to prevent gas from leaking out of the compressor casing along the shaft. The simplified seal oil system illustrated here includes a mechanical seal located around the shaft at the point where the shaft penetrates the compressor casing, and a labyrinth seal. The seal oil system also has a seal oil reservoir, which is divided into two compartments. The reservoir contains a strainer and an oil pump. The system also has a head tank and a check valve. During operation, the oil is pumped through an oil supply line and into this space around the shaft. The mechanical seal prevents the oil from leaking out of the compressor. The oil flows through the labyrinth seal and prevents gas from leaking out of the compressor along the shaft. The oil flows through the seal because the pressure of the oil is greater than the pressure of the gas in the compressor. The oil then flows back to the reservoir through an oil return line. As the oil comes in contact with the gas in the compressor, some of the gas is entrained in or carried along with the oil. The gas separates from the oil in one of the compartments of the oil reservoir. The gas rises up through the oil and returns to the compressor through a gas return line. The oil flows to the oil pump and is then returned to the head tank is used to supply oil to the seal if the pump fails. The check valve keeps the oil from the head tank from flowing down into the oil pump and forces it to flow through the seal. The head tank contains enough oil to allow the compressor to be shut down without a gas leak if the seal oil pump fails. The next components we'll look at are bearings. Two types of bearings used by most compressors are radial bearings and thrust bearings. Radial bearings support the compressor shaft. The bearings are lubricated to allow the shaft to rotate freely inside the casing. But the bearings prevent most radial movement, which is movement that's perpendicular to the shaft. Thrust bearings prevent axial movement, which is along the axis of the shaft. By allowing the shaft to rotate while keeping it in position inside the compressor, the bearings keep the impellers or blades from hitting the stationary parts and being damaged.